Okay, in this video I want to discuss products of collections of R modules and direct sums. Okay, so we start with a ring as before, so maybe not commutative, and I let I be an index set. So with that I just mean it can be any set you want. And I suppose that I'm given for each I in I an R module Mi. Okay, so I have some index set, maybe infinite, so it can be quite huge. And for each element, my index set, I suppose that you give me some R module. So then I can define the product. So the product I of Mi. So what is it? It's again an R module. So if I give you an R module, I have to give you three things: a set and two operations. So the underlying set is the set of all, just the usual product of sets. So all tuples I in I, where for each I in I, the element xi, it's an mi. This is just the usual product of sets. And addition is given by, well, if I have two such tuples, plus primed I in I, then I just add on all the coordinates xi plus xi primed I in I. So actually the underlying abelian group of the product is just the product as you know it in the category of abelian groups. And I equip it with the scalar multiplication given by this formula. So if you give me an element in the ring and a tuple, then I multiply on all the coordinates in this way. Okay, so this is the product module. So you can easily check that this is again an R module. One important thing to know is that this product comes with projection maps. So we have the let me call them projection morphisms, because they're again morphisms in the category of R modules. So for each I can make a mapping by I that comes from the product. So maybe I use a different letter now, so product of all j and I of mj to mi simply by sending a tuple to whatever it is on the ith coordinate. Okay, so it's quite obvious from the definitions that this is indeed a map of R modules. And just like when I talked about the quotient, the product module, it satisfies some universal property. So what is this universal property? So it says that for every collection consisting of some R module n and morphisms Fi for every I in I, so where n is an R module and Fi is a morphism from n to mi, there exists a unique morphism shoot my room. So there exists a unique morphism F and that is attached to this data that you give me. That goes from the product, that goes from n to the product. I and I of mi such that well, the obvious relation holds. So for all I in I, I have that the Fi, so the mapping that was given to me is equal to this universal mapping or this mapping coming from the universal property composed with the projection on I. Okay, so just as before as the quotient, I want to point out that this universal property characterizes the product up to unique isomorphism. So if you would have some other module that satisfies the same universal property, then you can play out these two universal properties against each other and get a canonical isomorphism between the two products. So in that sense, the product is unique to isomorphism. Okay, so the proof, I'll just give a very brief sketch that this construction indeed satisfies the universal property. And that's just, well, I just define this Fn, Fi, I and I of n to be, so let's go from n to the product. What do I do? Well, I send an element n to Fi of n. And then it's quite easy to check that this map satisfies the condition, and you also see that you really have no choice. So this is the only thing that you can define. That's basically the proof. Okay, so I want to discuss some examples of products. So especially if you do infinite products, what you get can turn out to be quite complicated. So for instance, you can take products of torsion groups and then end up with something that is no longer torsion. So for instance, example, I take I to be the natural numbers, and n. So for each natural number, I just take z modulo nz as a z module. And I consider the product over all n of z modulo nz. So even though all these individual things are torsion, this product module has some elements which are not torsion. So then, for instance, the mapping from Z goes to Z modulo nz by sending x goes to x mod n on every coordinate is injective. So even though all the modules, all the factors were purely torsion modules, the product thing has also some elements that are not torsion. For instance, the element which is 1 on every coordinate. Okay. Another thing you can notice is that this product is uncountably infinite. So leave that as an exercise. And z modulo nz is uncountable infinite. So it's a huge module. Second example. So it's a Chinese remainder theorem. For R modules. So recall that if you have a ring and you have two ideals which are co-prime in a suitable sense, then you can decompose R modulo the intersection of these two ideals into a product of two rings. And you can basically do this also for modules. So let R be a ring. And M R module and I, J, two-sided ideals in R such that I plus J is equal to R, so co-prime. Then you can define I times M to be the following submodule of M. So I just take submodule of all products I times M, where I is in I and M is in M. So if you think about it, you realize that this is indeed an R submodule of M.
Generated by these?
Generated.
Yeah. So you had these brackets for
yeah.
Right?
Yeah. So, and J times M is the thing generated like this. J,
M.
in the M. No. So then the Chinese remainder theorem says that if I do M modulo I intersect J, so that's again an ideal, so I can use the same definition for I intersect j times m. So this is isomorphic to m modulo I m plus m modulo jm by sending m to m mod I, comma m mod j.
Well, you write mod I and j, but that is I times m and j
I
times
times m and j times m. Okay, so you can decompose modules into products using this theorem. So the last example. So I take I any set, so that I in any set. Then I can look at the set of all, consider the set of all maps from I to R. So this is an R module because I can do pointwise operations, right? So if I have two such maps of sets, I can make the sum by sending I to f of I plus g of I, and similarly, if I have a scalar in R and some function like this, then I can define the scalar product as the mapping coming from I to R just by sending R times f of I. Okay, so this is a very natural way to make out of a set an R module. So indeed this is a functor. So then this is a functor, so we go from sets to rings by sending a set I to sets I comma R. It's a functor. And how it relates to this product is just that, so the relation to the product is just that we have, that if I take the product of copies of R, where I just, I made so I started by saying that if you give me for each index element a module, then I can make a product. So I'm saying now take for each index just the module mi to be equal to R, and I can make this product, and this is the same thing as the set of all maps from I to R, right? Because if I have such a map, I just send it to the tuple consisting of all the images. And yeah, you also know conversely, if I give you such a tuple, then it is a map of sets. Okay, so this is an isomorphism of R modules. Okay, so that's what I wanted to say about products of R modules. So we can also make direct sums. Erase this. So direct sums. More fancy language, one would say maybe co-product. Leave that to David. So direct sums of R modules. So we start again with a ring, so let R be a ring. I index set. And mi an R module for each I in I. So I defined this product. So maybe it's a definition. If mi I in I is in this product, then I call the support sub of mi, the tuple, to be the following subset. So I just take the set of all indices I in I, where this tuple vanishes, or does not vanish. So where mi is not 0. So it's a subset of I. Right. So if you think about this last example that I gave, where I viewed product of copies of R as some real set of functions, then this notion of support is exactly the same. So it's all things where the tuple is not 0. So the direct sum. So now I can define the direct sum. So that's of the mi where I is in I. So this is this thing. So it's actually a submodule of the product. It consists of all tuples mi, I in I, whose support is finite. So they are all the tuples in the product. Oh, now I have missed some in the product. And I, such that the support of the tuple is finite. So they are all tuples which at almost all the coordinates are equal to 0. That's the direct sum. So it is quite easy to see that. So we check. If I have two tuples, mi, I in I, mi primed, I in I, if these have finite support, then mi plus mi primed also has finite support. Right? Because suppose the support of the first tuple is some subset A, the support of the second tuple is some subset B, then the support of this sum is going to be a subset of A union B, which is a union of two finite sets, so it's a finite set. So similarly, for the scalar product, if mi, I in I has finite support. Then R times mi I in I has finite support as well. The other support can only become smaller. So this shows that the direct sum is an R submodule. And of course, if this set I is infinite and these modules mi are almost all non-trivial, then this is going to be really a strict submodule. It's really a smaller thing. But maybe let me record, maybe as a remark. So, remark, if I is finite, now if we're just doing finite products, then, yeah, you see it from the definition, this condition is an empty condition. So the direct sum I and I is equal to the product.
Okay, 3 minutes.
3 minutes. Okay. So I guess I'll end with a universal property. So universal property. So let's write Ji goes from mi to the direct sum. Okay, direct sum ranges over k, I, and k. For the natural inclusion. Yeah, so that's just a map that sends an element m in mi to the tuple, which is 0 for all coordinates that are not I, and at the coordinate I put m. Yeah, so in this way I can make a map from mi into the direct sum. This is an injective map. So then the direct sum satisfies the following universal property. So let n be an R module.
There's 1 minute left.
Oh. Okay, so maybe we got it and then
Okay.